Okay. So thanks a lot, Catherine, for giving me this opportunity. And basically what I'd be talking to you about are galaxies and their structures. And typically the work, I'll talk about some research work which I have done in galaxies, because that could probably give you an idea of what kind of work you could also plan to do in the future, right? So galaxies, you're all aware, are basically a collection of 100 billion stars, right? Plus there's gas and there's dust in the optical light, and you have dark matter too. But we're not going to talk about dark matter at all. So the typical masses for galaxies is about 10 power 9 to 10 power 12 times the mass of the sun. The sizes are about 100, like this is the size of the Milky Way itself, which is 100,000 light years. And so, which is approximately 30 kiloparsecs in size. And I'm sure you're aware about this. What is a light year or what is a parsec? I think you don't know the definitions, right? What are these things? Okay. So I don't know how the skies are in Belgium, but in India, it's very difficult to get a sky of this kind where you can actually see the Milky Way. So if you are in a nice dark sky, you can actually see the band of stars in the sky, which define the Milky Way. Now, so studying the Milky Way is essentially a very difficult problem because we are inside it, right? It's, for example, if you are inside a building or inside a house and you want to draw a picture of the house you are living inside while you are inside it, that's a little tough, right? And that's the problem with the Milky Way galaxy again, that because we are inside the galaxy, right? It is very difficult for us to understand the structure, right? So there are various methods through which people study galaxies. Now, Herschel, these are the amount, this is one of the earliest studies of the galaxy. What he assumed is if you assume that all stars have the same brightness, and the difference in brightness is just because of the distance to the star, he actually made some kind of a picture of the galaxy, which was something like this. But actually in today's times, we know that what Herschel saw was a very small portion of the galaxy, the very neighborhood of our galaxy, because we know that we do not see this part of the galaxy, especially in the optical, right? In optical light, we cannot see it because there's so much of gas and dust between us and that part of the galaxy that we cannot see it, right? So Herschel, the principle he used was a simple one. Assuming that stars have the same magnitude brightness, you can actually find the distances, but that was not actually right. This assumption, number one, is not right, that all stars have the same brightness. And number two, he did not count extinction. I hope you know about extinction. Extinction is the amount of absorption of light which happens because of the gas and dust in the galaxy. Now, it was not a long time back where, there were many, we discovered that we belong to a galaxy, and it's, just 100 years ago that in 1922, right, 100 years ago, when people actually discovered that the Milky Way was only one such galaxy and that there are many such galaxies in the universe, right? Till that time, till 100 years ago, people actually did not know. They actually thought that the Milky Way is the sun is, earlier, 400 years back, what they thought was the sun was the center of the universe, right? The heliocentric theory, where we thought the sun was the center of the universe. And much later, with Copernicus, we actually, this thing that you have, I'm sorry. We thought that the earth was the center of the universe, right? And much later, we realized that it was the sun. And then earlier, about 100 years back, Shapley discovered that the sun is not at the center of the Milky Way. And then with various arguments, I hope you are aware of the work of Hubble and Humason, right? So Hubble actually observed various galaxies in the universe, right? And he observed Cepheids. I think you know about Cepheid variable stars. This is a special class of variable stars. So the advantage of Cepheids is that Cepheids have a certain time, a period with which they pulsate. The pulsation is because the size of the star increases and decreases, right? It pulsates. And the pulsation time can be observed. Now, there is a direct relation between the pulsation time and the absolute brightness of a Cepheid variable. So if you observe a Cepheid variable and you find out its pulsation time, you can find out its absolute luminosity. Now the apparent luminosity is what we observe, right? And when we compare the apparent luminosity and the absolute luminosity, we can find the distance to the source. So what Hubble did in his work, when he observed Cepheid variables, he actually found the distances to these various galaxies, right? To these various objects. And that's when it was realized that these objects are outside the Milky Way. They are not within the Milky Way because the distances are so large. Now, what is our Milky Way? Our Milky Way is a spiral galaxy. There are many kinds of galaxies in the universe. So it's a spiral galaxy which has spiral arms as well as a bar. This is a bar, okay? Now, one very important thing for you to realize that when you look at a galaxy image like this, right? This is actually a dynamic picture. All these stars are moving in some orbits, right? And as they are moving in orbits, you see them like this. For example, if you had a galaxy which was like a sphere, right? An elliptical galaxy. That basically means that all the stars are going around in all different angles, random angles. And that is why when you look at the galaxy, it looks like a ball because the orbits are at all angles. When you see a disk galaxy, a galaxy like the Milky Way, it's basically telling you that the stars are going around the disk, right? Most of the stars are going around the disk in the plane of the galaxy. There are only a few stars which are going perpendicular to the plane, right? So you always have to remember that when you're looking at a galaxy, you are actually looking at the effect of the orbits of the stars, the orbits and the positions of the stars. That is what basically gives a galaxy its shape. The shape comes because of the orbits of stars. So if you look at our Milky Way, we have a disk. So in the disk, all the galaxies, all the stars are moving in a plane. And this is called the halo of the galaxy, where the stars move in orbits which are perpendicular or randomly placed. The galaxy also has a bulge, which is this part. And all these make up the galaxy together. So you have a disk, you have a halo, you have a bulge, right? And this is the approximate size of the Milky Way, and which is given over here, right? Now, some of you all may have heard about the Galaxy Zoo project, which was a citizen science project. In the sense, non-astronomers could also participate in this project. And what they basically had to do is look at various galaxies and describe what is their shape. So what is their shape? We also call that the morphology. Morphology means what is the shape of the galaxy. For example, this is a spiral galaxy, right? This is an elliptical galaxy, and this is a barred spiral galaxy. So you can have different shapes of galaxies, or what are called morphologies. And based on the shapes of galaxies got classified with the Hubble tuning fork diagram, okay? So the Hubble tuning fork diagram was a diagram made by Hubble to classify galaxies based on their morphology. So here he placed what are elliptical galaxies, which are more rounder, spherical kind of galaxies. And then they are the ones with the disk and the spiral arms. So these are the spiral galaxies, and these are the barred spirals, okay? And here he placed what are called irregular galaxies, which do not have a very clear shape. And Hubble thought of it that probably there is some kind of an evolutionary sequence, that galaxies move like this or they move like this. And in that way, we can explain the evolution or the formation of galaxies, right? But that has not been possible. The other thing I'm sure which you are aware of is that galaxies also have black holes at their center, right? And what is actually found is that there's a correlation between the black hole mass and the bulge mass. So depending upon what is the mass of the black hole, the bulge mass accordingly increases, right? So in a way, if you find out the bulge mass, you can find out the black hole mass for a given galaxy. Now the bulges are very interesting in galaxies. There can be different kinds of bulges. One is a kind of bulge which is called a classical bulge. A classical bulge is a spheroidal round bulge where you basically do not have any features. There are no spiral arms, no bars, etc. And basically it means that the stars have orbits which are randomly oriented, and hence these are called kinematically hot. The velocities are large, and therefore these kind of galaxies are the ones which are caused by mergers. Another kind of galaxies are what are called pseudo bulges. We'll be talking about them very soon. And these are bulges in galaxies which are in disk-like galaxies, where you actually see structures like bars and arms, etc. And the stars do not move so fast, okay? And therefore, these are galaxies which formed by what is called secular evolution. That means the galaxy evolved on its own for a very long time, okay? And that's what we call pseudo bulges. Now, what's also done with the morphology is we can also draw contours to the morphology, with which you can say whether a galaxy has a boxy or a peanut-like morphology or whatever kind of morphology, right? These are also another way of studying it. So galaxies, like I already mentioned, they are classified as elliptical galaxies, or there are what are called exogalaxies. These are lenticular galaxies. And then there are spiral galaxies. So we can classify galaxies in these forms, right? Now we'll be talking a little bit about bulge formation also today, where, like I told you, there are bulges essentially in elliptical galaxies. Spiral galaxies do not have bulges. They have very small bulges, and therefore there is a parameter called the bulge to total ratio, which you can see is very high for elliptical kind of galaxies, but it is low for spiral galaxies, right? And classical bulges, they formed from mergers, and therefore there could be some differences between classical bulges and ellipticals. We won't go into those details. I hope you are all aware that our galaxy, Milky Way, is sitting embedded amongst a lot of other galaxies, which are dwarf galaxies very close to us. And there are constant interactions happening between these galaxies in the neighborhood in our galaxy, in the halo of our galaxy. And especially you all must have heard about Gaia. Gaia is the ESA satellite, which basically studies these stars in lots of detail. And Gaia has revealed a lot of interactions between these dwarf galaxies and the Milky Way. Now, the first work I'm going to talk to you about will be about galaxy clusters, okay? So you have a lot of galaxy clusters, that means groups of galaxies. And here two of the very well-known clusters are here. This is the Coma Cluster, and this is the Virgo cluster. And now galaxy clusters can be of different kinds. So for example, if you look at Coma Cluster, you have a lot of elliptical and exogalaxies. And in Virgo cluster, instead, you have a lot of spirals and ellipticals in the Virgo cluster. And you could have various processes taking place in these galaxies. Now I'm going to switch off to one of the works, which actually we have a PhD student who's working on this, and I'll talk about that. And this is the work.
Are there any questions?
Oh yeah. Let's take some questions before
Are there any questions?
proceed. Yeah.
Yes.
Yeah, please.
From on my end, the sound is not optimal, and that's the reason why we turned off the video.
Okay.
So we don't hear you all the time, but
okay.
I don't know how it is for the students.
I can hear you
so
very
that's why
clearly.
we love the video.
I can hear you very clearly. I don't know.
Great. Yeah. Just so you know that's the reason why we turned it off. But yeah. Are there any questions?
Yeah.
That's great. Yes. Students, can you hear? Can you follow?
Yes, it's fine.
Okay.
Okay, thank you. And in any case, since the recording is happening on Priya's end, I suspect also it will be.
Yeah, sorry. Should I be speaking slower, or is it fine? Should I speak slower? Okay. So can we continue? Do I continue? Fine. So actually, I'm now going to talk a little bit about the PhD work of one of my students who's working on the Coma Cluster, okay? And the idea is basically to give you an idea of, okay.
Yeah.
Sorry, I think, yeah, there's some issue with the net. I don't know, it's coming and going.
Yes, it's, I hope this, so yeah, it was, I didn't hear you for about 1 minute now. So, but let's try to continue. And in any case, the recording is happening on your site. So that's a good thing.
Okay.
Students, if you have questions, then please type them in the chat. And Priya, I have a question about what you said about the bulge to total mass.
Yes.
That you mentioned.
Mm-hmm.
Yes. So where did this come from, this way of classifying galaxies by their bulges? Why specifically the bulge? And in what way is this bulge to total mass important?
Okay. So, like the Hubble classification, right? It does not give you numbers, right? You cannot quantify quantities, right? And therefore, like that's what I'll even be talking about over here, is that when we actually talk about morphology, we would like to get numbers with which we can compare. Now, there are many different ways in which you can get numbers. I will talk about some of them now itself when I show you the presentation. But one of the standard ways of doing it is via the bulge. The bulge is considered a very good indicator of the formation process of a galaxy. One reason being, like I told you, the bulge is related to the black hole mass, right? And it is considered, we do not know very well the theory of formation of galaxies, but we know that most galaxies do have black holes in their center. And the very fact that the bulge mass is related to the black hole mass, this is a relation by merit. It's a very well-established relationship. And therefore, people are interested in knowing things about the bulge because that will give you an idea of the seed, the black hole seed, which probably has played a role in the formation of the galaxy. Now, amongst the many different ways of classifying galaxies, other than the Hubble classification, one way of classifying galaxies is by what is called the bulge to total mass ratio. Now, I'll explain how we actually do that. But what we basically do is you look at a galaxy and you have a luminosity profile. Now, we decompose the luminosity profile with a program called GalFit, with which you can separate the components of the galaxy. And the bulge to total mass ratio is an indicator of the morphological type. So typically, elliptical galaxies have bulge to total mass ratios greater than 0.8. Spiral galaxies have it less than 0.3. Lenticulars have it around 0.5. And therefore, what happens is with bulge to total ratio, you can easily classify a galaxy, even if you do not observe it that well, but if you can decompose it, you can actually get these things. So that is yet another independent way of classifying galaxies. So people classify galaxies in many ways, including this. And the powerful part about this is that this is a number compared to the Hubble type. In Hubble type, you don't have a number, right? So actually that's what I'll be talking about even in this work, that the idea is basically you want to describe the morphology with some numbers, right? Because then if you have numbers, you can plot it, you can do various things, look for relations between them, right? And therefore, yeah. So
there was a question by Vital. What is a black hole seed?
Okay,
good question.
So yeah, thanks. So we do not know how exactly galaxies form, but like I mentioned, most galaxies, including the Milky Way, have a black hole in the center. And now, you know, black holes attract mass, they hold the mass, right? They're the ones which will hold the mass. And therefore, one of the possible theories of formation of galaxies is that the black hole has some kind of a role to play in the formation of a galaxy. And therefore, it is often called a seed. right? Because it will be the seed which will help to collect more matter, which will make up the galaxy. Now with Gaia, I was telling you all about Gaia. With Gaia, it's also clear that the Milky Way has actually grown in time. The Milky Way has been constantly interacting with other galaxies, gobbling them up, eating them up, and that's how it has increased its mass. So what we now understand is that, at least for the Milky Way, it has gone from small to big. So you had a smaller galaxy, which then took in, which ate up many more galaxies, and then using that, it built up its own mass. And therefore, we think that, I mean, this is the present understanding, that we think that a galaxy basically has the black hole with it, and it actually kind of uses that like a seed, which will help to increase the mass of the galaxy. So the present understanding is that galaxies form from small to big. Catherine, maybe you can tell them what's a seed and whatever's the thing. I can't hear you.
Yes, yeah. I'm summarizing it in the. I'm summarizing it in the text in the chat, and you can, yeah, you can go over it and see if I'm doing it in the right way.
I can see the chat. I can see that fine. Okay, but that's a good question. But that's the, and especially for the Milky Way, we know that this is what is happening. We can't exactly generalize it for all, but astronomers like to generalize. It is not right to, but that applies for the Milky Way at least. Yeah.
Yes. Okay. Thank you very much. Any other questions? If not, we can continue.
Okay.
Ah, yeah. No, there is a question.
Great.
Very good question.
Yeah.
You can read it in the chat, Priya.
Yeah. So very good. That's it's a very nice question. Why are there in fact different types of galaxies? Does it have to do with the distribution of mass, where, when they were formed, or are there other factors? I wish I knew the answer. I'm sorry. We do not actually know the answer to this question. But like I told you, that the shape of the galaxy is basically a reflection of the position and velocity of stars, right? Now, why do stars have those kind of positions and velocities? We do not know that very well. But we know that, for example, in an elliptical galaxy, stars have velocities which are in all directions, randomly oriented. And therefore, you have an elliptical shape because the orbits can be in any angle, in any way, right? But for some reason, and elliptical galaxies are rotating. They are very much rotating. But you have the spiral galaxies, which are also rotating, but then all the stars are only on the disk. The majority of the stars are on the disk. There is a small bulge, but the bulk of them are all on the disk. Now, why do they choose to do that and not that is something we do not exactly know. But it is obviously because of the dynamics of the stars that this is happening, right? So we also do not know how do galaxies, we know that galaxies can change their morphological types, right? Like you can have two spiral galaxies which can form an elliptical galaxy, or you could have some, interactions of that kind. But we do not, so people do simulations. You can simulate the bodies, the stars, and actually with simulations, they can study what happens when two galaxies interact, right? How do the stars redistribute their orbits and their positions? That we can do with simulations. So people have various simulations to study that, but there isn't a single answer to your question. It varies. Yeah.
So it's a very good question.
Yes.
Okay, thank you.
Another very good question. There's another good question. Is the morphological classification purely based on observations on the optical spectrum? That's a very good question. So obviously, traditionally, astronomers like the optical bands, right? But obviously, there's a lot more information you can get in X-ray, in radio, as well as in the infrared. Because in the infrared, you'll see gas and dust. In the radio, you'll see that. In X-ray, you'll see the high energy sources which make up a galaxy. And therefore, the traditional Hubble classification is what is done with optical images, but definitely it does make a very big difference if you observe galaxies in different wavelengths, because then that gives you the complete picture, right? So when you look at it in infrared as well as in radio as well as in X-ray, you get a better understanding of the galaxy and the different components in the galaxy, right? So optical is there, but it's a good idea to look at it in other wavelengths. So Hubble classification is optical, but you can the second thing I'll be talking to you all will be about AGN, active galactic nuclei, and there you'll see we are going to be using X-ray data. So you may want X-ray data for some. Yeah. Yeah. Okay.
Thank you.
So are there any good? There are good questions. Good.
Very good questions.
Yes. What about somebody else? Is it fine? Yeah. Maybe should I proceed?
Maybe yes, please proceed. Yeah. If any questions come up, please post them in the chat.
Yeah. You're most welcome to interrupt in this thing. Okay. So yeah, and another important thing was that, so the important thing is that, like I said, what we wanted to do is, this is just a study of the core of the Coma cluster, right? So the Coma cluster, I showed it to you in that picture. And we basically tried to study the morphology of galaxies in the core to see what kind of galaxies are present in galaxy clusters. Now, what we also know is that, we will talk about these things, is that one way of actually getting the morphology is what is called visual inspection, which was like I showed you in Galaxy Zoo project. And the other way is we want to quantify morphology. By quantify, I mean to say, give it some numbers, okay? So what we basically do in that is we fit the brightness of a galaxy to various profiles, okay? And based on those profiles, we actually say what kind of a galaxy it is. Now we know that the property of galaxies can vary depending on their environment. And what we are basically trying to see is how do the properties of galaxies vary if they belong to a cluster. So this is again another thing of this. So there are different kinds of clusters of galaxies, okay? So some are galaxies where you basically have CD clusters. These are clusters which are rich in ellipticals. You have lots of ellipticals. Then there are what are called the spiral rich clusters, which have a composition which is similar to the field. By the field, I mean to say galaxies which do not belong to a cluster, right? And spiral poor galaxies are the ones which are dominated by SO galaxies. SO galaxies are lenticular galaxies. Okay, these galaxies, the galaxies which are somewhere between ellipticals and spirals are what are called SO galaxies or lenticular galaxies. Okay, so you have this third type, spiral poor, which is basically made up of SO galaxies. Now, Coma cluster is a very rich and dense cluster, which is at a redshift of only 0.02. But a redshift of 0.02 corresponds to a distance of 100 MPC, okay? So it's about 100 megaparsecs, which is the distance to Coma cluster. And hence it's a very good cluster to study for this thing, and it has been studied. So it is a CD type cluster, which basically has a lot of ellipticals and SO type of galaxies and very few spiral galaxies. Now, the data we used was basically data from the Hubble Space Telescope, okay? Now, the Hubble Space Telescope has various instruments on it, and one of the best imaging instruments, which is there on the Hubble Space Telescope, is called the ACS, okay? The ACS is the Advanced Camera for Surveys. So the ACS camera is on the Hubble Space Telescope, and this is the one which was used for imaging of the Coma cluster. So what was done is 25 different regions were actually observed with the ACS camera. And using that, this was done in 2 pass bands. These are 2 different pass bands of HST. One is called the F814W filter. This is a filter. And there's another filter called the F475W filter. So these are the two filters in which these data was taken. We are basically working on the data which is on the 814W filter. This is close to the I band filter which we have in our normal things. Right? So if you actually look at the Coma cluster, these are the locations. There were 25 tiles, and these are the locations of the 25 tiles from which data was got. Okay. So this is the region which we are studying of the Coma cluster. Coma cluster is much bigger, but we have only studied this region, which is there with Hubble. So this is approximately the location of where we studied. Now what was used is we used a software called GalFit. Now GalFit, what does it do is if you observe a galaxy, right, it breaks it up into its components. So the component can be the disk, the bulge, the point source, the various kind of things which are there in a galaxy, so that it can actually find out how much mass is there in the gas, in the disk, in the bulge, in various components of the galaxy. So we use this program called GalFit. And actually the next paper also uses GalFit. Both of their papers actually use GalFit. It's a very powerful, it's a very good resource. So what is done is, one of the standard things is done is you fit the profile to what is called a Cersei function. A Cersei function, which is given by, which is of the form of this kind. Okay. If this is the Cersei Index, which is 1 upon n, n is called the Cersei Index. If n is equal to 1, okay, then you can see that this function will then become what is called an exponential function. So you can say that the brightness is falling exponentially, right? So that is an exponential function, which is typically how galaxy disks, their brightness actually falls like an exponent. The bulge falls like what is called the Cersei. And you can even have a Gaussian function. Supposing you had a Gaussian function, n will be half. Okay, it will just be half. So you'll take 1 upon root, and that would be the kind of function. So what is basically done in GalFit is, supposing you have an image. This is the image, right? What GalFit does is it creates a model to the image. So it, for example, creates a model where it says that here is another model galaxy, which is exactly using the parameters of these observations, in the sense whatever details are there of the telescope, to tell me how much is there in the disk, how much is there in the bulge, etc. So this is what is called a model image, right? Now you do this is called the science image, the actual image. What I do is you take a difference between the science image and the model image, and you get what is called the residual image or the subtracted image. So this minus this gives me this, okay? Now here you can see that this residual, it has very nicely subtracted, there is nothing. That means this galaxy is an elliptical galaxy. But now look at this galaxy. You cannot see much over here. But when I fit the model and I do science minus model, you can see beautiful spiral arms, which you could not see over here, but you can see it in the residual image. Here you can see this is a spiral galaxy for which we make a model galaxy. And now you can see in the residual, it's so beautiful, you can actually see a bar, right? So what actually GalFit tells you is it breaks down the galaxy into its components, and you can use that to find out the structures which are there in the galaxy. So you can find out the spiral arms, you can find out the bars, you can find out if this galaxy has 2 nuclei. There are sometimes galaxies which have 2 nuclei. Okay, there are 2 nuclei because maybe it formed from a merger or something like that. So you may have various things like that which actually cause these things. I can see, okay, this is Catherine. I thought there was a question.
There's a few questions, exactly, yes.
Okay.
So you can answer them. These are questions.
Yeah, thank you. Yeah, very good. Thank you. So I can see the questions. So why was the particular filter next to I band? So actually what happened is the longest exposures were taken with this filter, which is the I band filter. And the I band is a very good filter because it is you know, it's longer wavelength. So if it's longer wavelength, there will be lesser extinction, right? So you will be able to see through gas and dust, right? So the idea is that to get a better image of that galaxy, if you take it more in towards the infrared, you are going to get a better image of the galaxy. If I were to take this, for example, in ultraviolet, right, in shorter wavelength, then what happens is, because the wavelength is short, I hope you are aware that extinction is inversely proportional to wavelength. So if my wavelength is very short, I will, a lot of light will be lost in extinction. So 814 actually is 814 nanometers. Okay, so it's a long wavelength, and that's why you'll have lesser extinction. So it's better for you to see the galaxy in that. And that is why the Coma Cluster survey, which was done with HST, was planned with longest exposures for 814W filter, so that you could get the best results, right? So yeah, so thanks. I think Catherine, you've written the answer. Longer exposures for this, basically because that would be minimum extinction, right? So you'll be able to see through the gas and dust. Yeah. So, okay. So what we basically did is there are about 219 galaxies which were there in this Coma cluster, right? And what was done is that for all these galaxies, we actually did this kind of a thing where we broke the galaxy into its components and got its morphological type, right? The other important thing we had to do is we needed to find out which of these galaxies are members of the cluster. How do we do that? We do that using spectroscopic redshifts, right? So you have, for the same data set, you have spectroscopy done with which you get the redshift. And once you get the redshift, you apply Hubble's law, right? You know V is equal to H into D, right? So if you measure V through spectroscopy and you know Hubble's constant, you can actually find out. So here's Hubble's constant, 69.8 plus minus 0.8. So you can use that to actually find out the distance to the galaxy and find out whether the galaxy is a member of Coma cluster or no. See, there can be many members which are lying in that part of the sky, but they are not members of Coma cluster, right? So you basically, first of all, need to filter out which are your members and your non-members. Because what is our job? We basically want to compare the morphology of members versus non-members so that we can see that how does the morphology of galaxies change if they belong to a cluster. That's what we want to see. How does the morphology change, right? So what we do is we use these spectroscopic redshifts and we ended up with 3 categories of galaxies. Some galaxies which were the members, some which are not members, and then there are a whole set of theirs which are unknown redshift, for which we don't know the redshifts, okay? We also classified galaxies into 2 types, one which is called dwarfs and non-dwarfs. Now, dwarfs are also a very interesting class of galaxies because it is seen that these dwarfs are very important. They play a very crucial role in galaxy formation, right? So what was actually done in this other paper, older paper by Marinova, said that if you want to categorize for Coma cluster, the dwarfs and non-dwarfs, you have to check the absolute magnitude of the galaxy. And all galaxies that are fainter than minus 18.5, all these are dwarfs. So we actually did it to check in our sample which galaxies are dwarfs and which galaxies are not dwarfs. So this can obviously be done for cluster members because we know the distance. We have to convert to absolute magnitude, right? So we can do it for cluster members, we can do it for the non-members, but for unknown redshift galaxies, we cannot find out whether they are dwarfs or no, because we don't know how to find out their absolute magnitudes, right? So we found out in our sample of 219 galaxies, we have 134 members, 52 are non-dwarfs, 82 are dwarfs. And the non-members, 32 are non-members, 4 are dwarfs, 28 are non-dwarfs, 56 are the ones we don't have. So you look at this in the cluster itself, you can see that the bulk of the galaxies are dwarfs, right? They are very important components of clusters of galaxies. Oops, I'm sorry. So this is approximately the classification which we did for all the galaxies. These are all different morphological types. This is elliptical, lenticular. CD is one big galaxy which is sitting in the center over there. There are 2 such galaxies. Only one is there in our data set. These are the ellipticals SBOs, the lenticulars. This is the barred lenticular, spiral, barred spiral, ring galaxies, irregular galaxies. So we actually categorized all our galaxies into all these different types. These are all the non-dwarfs, okay, for which we actually have all this stuff. We also found out, because we've done GalFit, we found out the bulge to total ratio. And you can see the bulge to total ratios, which for different, and they can actually be used to find out different morphological types. So this is one earlier paper in which also we did it. And so you can actually see that the bulge to total ratio, what Catherine was asking earlier, can also be used to classify galaxies exactly in the Hubble style. So you can say, what are the values of B/T for ellipticals, for SOs, for spirals, for various kind of galaxies. You can find out the bulge to total light ratio, right? And what we did is we studied the distribution of bulge to total light ratio for the cluster members. We also did the color of the galaxies. So we, if you remember, I told you there was also data in 475, another band, which is F475. And using that, we found out the color of the galaxies. So like you do it for stars, this is the color magnitude diagram for galaxies. Now, what you can very clearly see in this, these stars, these ones are the dwarfs. The red ones and the pink ones are ellipticals, okay? And you can see it over here. The SO and SBOs are the yellow ones. And the blue ones, you look at these, this one is, these are all spirals. The blue ones are spirals. The green one is a barred spiral. Now, what you can see is on a color magnitude diagram, very clearly, see, these are all the members. The crosses are non-members. So you can see that they are clearly not sitting on this. For the simple reason that we do not know what is their distance, right? These are all at the same distance. So they are all occupying the same region. But all these galaxies, we don't know. So we don't know how to push them up or down. The open circles are the ones for which we do not have the redshifts, okay? So the crosses are the ones for which they are not members. And the round open circles are the ones which are unknown redshifts. And the members, you can see, they beautifully sit along this line, right? This line is the line where the members are sitting. So you can clearly see a color magnitude relationship for galaxies. So similarly, if you do color width versus B/T, you can also see there's a clear relationship. That means as the B/T, these are elliptical galaxies. These are spiral galaxies. So you can see elliptical galaxies, they have larger B/T because elliptical galaxies have a large bulge and they are redder, right? They are up over here. This is red. While spiral galaxies have a smaller bulge, they are sitting over here and they are bluer, right? So spiral galaxies are bluer and they're sitting over here. Elliptical galaxies are redder and they're sitting over there, right? And in short, here we have another plot which actually shows you different morphological types versus the distance from the center, right? So you see closer to the center, you have lenticulars. These are all lenticulars. This is elliptical. And these blue galaxies and green ones are the spirals. So the spirals are on the outside and the ellipticals and lenticulars are towards the inside, okay, of the Coma cluster. And you can see in general, color relates to age, metallicity, and various other factors, right? I won't go into too much more details, but okay, a little bit more, very little bit more. Like I said, when we fit it, we get what is called the Cersei Index. Now, the Cersei Index is also used to classify galaxies, either as dwarfs and giants, as well as to know whether the galaxy has what is called a classical bulge, which formed by mergers, or a pseudo bulge, which formed by evolution on its own. So we also, in this work, we are also doing Cersei Index with B/T, and we do various other things. So I think I should stop over here because that will get you confused, because this whole thing is basically part of a PhD, which a student is doing, which our deadline is to submit it by June. So we are now working on this. So I don't want to confuse them with too many things because there's lots more in this. But I think I should stop, right? I should stop.
Well, I think you already gave so much very interesting info. So maybe we can take some questions. I already wrote down some questions that came up. when you were explaining, it was
Very good.
very super interesting. So one of them was, when you make these model images with GALFIT, what are the input parameters to make these model images?
Okay, so GALFIT, actually you have to give it initial parameters, okay? And the initial parameters are, for example, if you fit it in different components, so then you have to give it the magnitude of the component, the radius of the component, you have to give the position angle, that is the angle at which it is there. You have to give the B by A, the major and minor axis. So there are various parameters you give for GALFIT. And there are smart ways of doing it, because the problem is you have to understand that you're fitting so many parameters, right? So you can get a minimum chi-squared for many different combinations of parameters which need not be correct, right? And so the problem is each component will have 5-6 parameters. And if you're fitting 2 components or 3 components, right, then obviously the errors are going to be very large. And therefore there are some typical techniques in which how do you ensure that your GALFIT gives you a good result, because it like I said, it's multi-parameter, so you can go wrong. So there's a GALFIT page, a website, you can Google GALFIT and see it, and there is very detailed description on that page as to how exactly you do GALFITting and how do you, how should you do it. It would take a lot of time.
Sure,
and
sure.
I can see another question is, how is B by T determined? So B by T also is determined using the GALFIT output. That will tell you how much is there in the bulge, and you know how much is there in the total, and you use that to do it. What's interesting is, parameters like the B by T does not depend upon distance, right? Because both the components will have the same effect because of the distance. So B by T is independent of distance. Similarly, Cersei Index, the fall of the brightness, that also does not depend upon distance, because distance will just scale it up or down, right? It will move it up or down. But the shape of the profile will remain the same. And therefore your Cersei Index will also remain the same. So similarly, even the color, we spoke about color also, which was F814 minus F475. Color is also distance independent, because both the wave magnitudes will get shifted by the same amount, right? So now you see that with these parameters, we are actually getting something with which we can quantify the morphology, which is distance independent. Now, I can see a question, so I'm jumping to that. What is the reason why some galaxies do not have redshift? Because basically you need to do spectroscopy for the galaxy so that you get redshift, right? And spectroscopy is a difficult job because you are only collecting light in a particular wavelength. So you need a very big telescope to do spectroscopy for a faint source. So if your galaxy is not very bright, then you may not be able to do spectroscopy, because you will need to observe it for very long. You will need to have a very long exposure time to try to observe that galaxy, either long exposure time or a very big telescope. And therefore, generally what you will find is that for galaxies, the brighter galaxies, you will have spectroscopic data. But otherwise, if the galaxy is on the fainter side, you will not have spectroscopic data. And that's how for our sample, for 55 of the galaxies, we do not have spectroscopic data, right? And because we don't have spectroscopic data, we don't have the distances. Simply because either those galaxies are too bright or somebody has got to observe them, right? So somebody should observe them. Like I said, with a big telescope and with lots of exposure time, you need to have both, right? And that's a difficult job. So that's how we don't have redshifts for all galaxies. B by T is okay with these, this thing, yeah. So now we have actually moved to quantifying morphology in distance independent ways, which are very important because it is not very easy to find out the distance to everything, right? That's a difficult job.
That's a hard job in astrophysics. There was one more question that I had, which is related to the GALFIT, because you can make the spirals visible, for example, by taking the residuals.
Yeah.
So the GALFIT doesn't fit spirals, right? You don't.
You can do that. So if you want to find further substructure in the spiral, then you can model the spiral arms and then look for further substructure within the spiral arms. But the only problem in that is, like I'm saying, the more components you make, the more parameters you'll get, the more free parameters you get. And that's why then when you fit it, the errors, etc. and all can be larger. But people actually do that. And specifically, for example, if you want to find the bar, right? If you want to look for a bar, you can model the bar also for the galaxy and you this thing. The next paper I'll tell you, that's also with Galfit, but I'll tell you what we did in that. And so yes, you can in principle model every parameter so that you can see further, further details. But there's a risk in doing that. The more components you fit it, the more, the problem is if you find a local minimum, there's a local minimum in which it fits, then the Galfit will stop. It will stop with that and not fit anything more. But that may not be the right fit. Right? So that's the problem. Yeah.
Okay, thank you very much. Are there any other questions?
So actually we are soon submitting these things. Actually, some of these papers are still in process. So when they come, I can actually share it with students and they can see. So there is more stuff, but I think that'll confuse them. Let's stop with this, right?
Yeah. Okay, thank you. Are there any other questions? No questions?
Please feel free. I mean, I'm sorry if I got you a little confused, but my idea was to basically show you how, how you can actually use, your information about morphology to study much deeper things, right? Other than, it's not just looking at the galaxy. It is much more than that.
Yeah.
Right.
Okay. Thank you.
Should I proceed with the next one or?
Yes, so there is one question related to the Cersei Index.
Yes.
Which you mentioned, which is the way of fitting the galaxy. So maybe could you briefly repeat?
Yeah, okay. So that's not a problem. I'll just now show it to you. So the Cersei fit is just the, where is the thing? Okay, here, it's here. No, it's not here. One sec, I'll just open that thing. I think I closed it. 1 second, okay. Oh. 1 second, just a minute, I'll just share that thing.
Yeah, take your time.
Oh yeah, okay. No, I have many windows open, that's why I'm confused. Okay, so the Cersei Index is,
I know.
Yeah, so if you remember when I told you all about, you can see my screen, right? Okay, this has gone here and here. So the Cersei Index is just the power. I'll just show you. Yeah, okay. So this is the brightness of the galaxy, right? As a function of R. As a function of R, we are seeing the brightness of the galaxy. And we fit it to this kind of a function. So you provide Galfit with the IE value, which is the brightness of the galaxy, and the RE, the effective radius. Now you use that to actually fit and get the value of N. And N is called the Cersei parameter, right? So what I'm going to also do is I will show you another thing. Just a minute, just give me a minute. And